Hi, welcome back to CSS 373. Now we're going to talk about determining if the given tree is LLRB tree or AVL tree or if it is both. So this is our first example, so please take time to think about it and come back to solve it with me. Okay, so the question is this actually an LLRB or an LVL or both, right? So the answer for this to be LLRB tree, this is actually correct because we know that for a fact that there are a few invariants that we need to check. The very first thing is essentially also the one of the easiest is checking if there are nodes with no two right links. So we can see that all the right links are on the left side. That's also pretty important to that it must be on the left side because it's a left leaning right black tree, not right leaning left black tree. So we can also check this other important variance that every leaf node has same number of black links. What it really means is there are 1 and 4, 1, 4, and 6 as a leaf node, and they only have a one black link pointing to them. So for example, 6 is being pointed by one black link, and so is 4 by 3, and 2 is being, and 1 is being pointed by this only one black link as well. So that's very important invariant to check, so please don't forget. And lastly, it is BST. You can check this using recursive definition that, okay, 6 is greater than 5, and then we can say 3 is less than 5, whereas 2 is less than 3, and 1 is less than 2, and 4 is definitely greater than 3. Then we know that all these invariants check out. So the next question is this actually a valid AVL tree? The answer is, unfortunately, it's not, because we would know that our AVL has invariant that really emphasize the height, the difference, the maximum height of the tree, right? So we can see that here, the maximum height, let's look at this subtree first, because on this left subtree, let's look at this first, actually, I guess. So then this difference is 1 and 0, so that's 1, that's okay. And then now we'll expand to actually this whole subtree. And we can say that, okay, this and 3 and 4 checked out, so that's okay. And then now we can say that, okay, 0, 1, 2, and height of 1. Then 2 minus 1 is 1, so we're good to go. So then we know for a fact that we have checked this small subtree, and we have checked this. So then we know that this is like 100% good to go as a height. Then now we can look at this saying, okay, the maximum height recorded on the right subtree was actually only 1. So then what we have recorded here is 0, 1, 2, 3. 3 minus 1 is actually 2, which is greater than 1, which is our maximum difference that the AVL tree can have. So we know that this is actually not a valid AVL tree. So really try to break it down into smaller portion of the trees, because this example is pretty simple, but when the tree is pretty big, it could be pretty challenging to just kind of like eyeball it and get the height of it. So okay, so then the second example is the same question. Is valid LLRB and valid AVL? Sorry, LLRB is hard to say. So the answer is actually this is not. So I need to think about it a little more. That's why I put the slide here really randomly. So if you were not quite sure, so please read this one more time, and then solve it with me. And one other thing is there is actually a video about LLRB tree and LVL tree properties. So make sure you watch that and solve this as well. And also lastly, these drawings are super helpful, like I said in the previous video, because they're essentially like literally counter example of this invariance, like saying like why, like when it is invalid. So make sure you understand both drawing and the writing as well. Okay, so this is not because this is one of the big invariants that kind of we talked about for LLRB tree, that the leaf nodes needs to be pointed by the same number of black links, but in this case that's not the case. So you can see that here there is 6, 11, 42, and 63 is a leaf node. You should be familiar with leaf node. Leaf node means it's just a node that doesn't have any children at all. So they're like usually on they're always on the like very like you can think about like they're usually like on the bottom of this like tree. Okay, and you can say that, so this 11 actually has black links, right? So we can say, okay, this has 1, 2, 3 black links. Whereas 63 actually has only 2 black links pointing to it. And 6 is actually even worse, right? Because there is only one black link pointing to it, because the red link doesn't count when we count black links. So, so this is not a valid LLRB, unfortunately, but to answer the AVL, please read this and then understand the drawing and the writing. And we know that this is, based on the previous example, that this is correct AVL because we can see that the height is actually only differ by maximum of 1. So how do we know that? So we can take a look at this portion first. So the height is actually difference is 0 on this small subtree. And you can kind of see, okay, what about the left of 6? Then it differs by only 1, so that's okay. So yes, so there's only level 1, so that's okay. And then now we would see this whole subtree. And we would know that this 0, 1, 2, and then this is height of 0. So 2 minus 1 is 1, so we are good to go. So this is always how you should check like AVL. I think it's kind of recursive function that, okay, now everything checked out here and here and here. So then we know for a fact that this is valid. And then let's move on to our right. And then the maximum that was here was 1 minus 0, so that's 1, that's okay. And now you can see that 1 and 2, so this whole like tree here is actually height of maximum 2 here, right? 0, 1, 2, whereas this was 0, 1, 2, 3. So 3 minus 2, oh, don't forget to put absolute value because it doesn't matter like which like left subtree or right subtree is like has a like greater height as long as it's only differed by 1. So it's okay. So we're good to go so that we would say this is a valid AVL tree with the height difference of 1. Yeah, and we know that also this is, you always need to check if they are valid BST as well, because LLRB and AVL both must be valid BST tree. So what it means is you can see 43 is greater than 7, and here that 7 is greater than 6, that's twice on the left, and so on and so forth. So yeah, make sure you understand those drawing and the previous drawings on their properties, this one and this, and make sure you can identify in real life example that we're providing to you in a tree format. If you have any other questions, please post it on ad or let us know during our office hour.